Hello friends, welcome to session 16. The topic of this session is feature engineering. Let's see what feature engineering is. Okay, so here is the agenda for today's discussion. We are going to begin by talking about what is feature engineering and why is it important. Of course, a lecture on feature engineering would have to begin with what it is and why it is important, right? We are then going to move on and talk about something known as principal component analysis, okay, or the PCA. PCA is an important idea in machine learning, and we are going to spend considerable time talking about what PCA is. We will then talk about a related idea called LDA, known as linear discriminant analysis, and it is also called normal discriminant analysis or Fisher discriminant analysis. So we are going to study about LDA as well. And finally and very briefly, we are going to be talking about kernels. So this is going to be the agenda for today's discussion, and let's get started. Okay, so what is feature engineering? Now, when we are going to be talking about feature engineering, I want to clarify upfront that when I talk about features, I mean the independent variables or the columns of your data. So you gathered data, you want to run a machine learning algorithm, the independent variables also the columns of your data are known as features. And feature engineering pertains to these features. Feature engineering basically asks the question, how do you modify the features or the data to get better results? Okay, so what sort of pre-processing, what can you do to the features or the data so that your models deliver better results, right? So feature engineering concerns itself with doing some pre-processing or doing something to the features or the data so that your models work well. That's feature engineering. Now, here is an example that we have seen many weeks ago. And this example was, where we talked about getting information about job candidates who have applied to your company, tabulating some of their features or independent variables, and then doing a binary classification on whether to shortlist a particular candidate or not shortlist that candidate. So a binary yes-no classification. And this was the tabular data that you gathered. These were candidates, the rows were candidates. And the features or the independent variables that you had tracked were marks, okay, maybe the graduation marks, BCom, BA, whatever it is, the amount of experience the candidate has, his current salary, and you threw in an attribute called attitude. Okay, so when you sort of briefly spoke to the candidate on phone, you got an idea of what kind of a person that is, and you put in some sort of, you put in some descriptors there. The first column was a ID column, something that uniquely defined each candidate, could be his PAN number, could be his, any other identifier. And this was the sort of data you had, right? Now, feature engineering is going to concern itself with pre-processing this data that you have and also looking at what columns or what features are the best to use in order to make your shortlisting decisions on these candidates. Okay, so that is what feature engineering is. Going back to the diagrams that we have been seeing so far, let us say you began with this data. If you began with this data, you were interested in doing binary classification, and you would come up with the best separator like this, which would give you certain amount of in-sample error and certain out-of-sample error. Right? So this is what you would do. Now imagine a situation where you were to transform this data. So that it starts looking like this. And if your data actually started looking like this, you would do a much better job of coming up with a linear classifier. So you would like to have data that looks like this, right? That goes without saying. And therefore, if you wanted the data to look like this, you would have to do some feature engineering to go from here to here. Here is another example. Let us say you had data that looked like this and you had to do a binary linear classification. Now clearly on this data, binary linear classification is not possible. But if you were to come up with a feature, instead of these two features x and y, instead of features x and y, let's say you came up with a feature which was, distance from the origin, you could perhaps come up with a better classification than simply using x and y, right? So I'm giving these two examples to show that there are things you can do with the data, with the features that you are using, so as to deliver better results with your model. In other words, what I am saying is the following. There are various ways to pre-process your data to enhance model performance. Okay, this is entirely intuitive. You can believe that there are ways to pre-process your data to enhance model performance. You can modify the features, potentially giving better results. This is an example of that. You can modify the features themselves. So pre-process your data, modify the features to give better results. And finally, you can believe that the techniques that you apply for pre-processing or for modifying the features would depend upon the model you select, and it may involve experimentation, right? So some technique that works for a particular type of a model may not work on another type of a model, and you may actually have to do some back and forth, do some experimentation, use validation sets and so on to identify the best ways to perform your feature engineering for your problem, right? So this is what we are going to talk about. We are going to be talking about how to pre-process your data and how to modify the features at your disposal. Okay, let's look at the simpler of the two, the data pre-processing. And some of the things that I'm going to talk about over here are fairly straightforward. They are fairly intuitive. They are fairly obvious. Okay, but in the interest of completeness, let us see how you would pre-process your data. We have hinted at some of these things in our earlier lectures on linear classification, linear regression, etc. But like I said, for the purpose of completion, since these are aspects of feature engineering, let's talk about what these are. Okay, so again, looking at the same data that we had, shortlisting candidates for a job, and this was the data about the candidates that you had gathered. Here are some of the things that you may want to do with this data. So missing values and interpolation. Okay, missing values and interpolation. It often happens that your data that you have gathered is not complete. Okay, for whatever reason, measurements, went faulty, or if this was a human exercise, somebody forgot to do something, so on and so forth. So for example, here is a candidate 2 whose salary was not captured, or here is a candidate 6 whose attitude was not captured, so on and so forth. And what you need to do is look at any such missing data, and usually this missing data is filled by a process of interpolation. So how you would interpolate is you would look at the other attributes, see the nearby linear attributes, and do look at the nearby, the candidates who have nearby attributes, and then do sort of a linear interpolation to fill in this number. Okay, some numbers may be, some attributes may be harder to fill, but a process of locating missing values and performing an interpolation is something that you need to do upfront on your data if your data is not complete, as is usually the case. Deduplication. Now often, measurements are taken multiple times, and there might be duplication of data points in your data, and this can of course tilt algorithms or your models to behave in one way vis-a-vis another. Now for example, here candidate 3 and candidate 4 look like a duplicate of each other, except that here some extraneous term has been put in for salary, which is not the case over here. And you may want to delete one of these rows in order to sort of ensure that each candidate is captured only once. So this is deduplication. Again, something fairly straightforward and something that you can understand. Feature scaling. Now, this is something that we have alluded to when we did linear regression, linear classification. And what it refers to is that the numerical quantities, it's always good to have all the numerical quantities be roughly in a same dynamic range. Okay, so your salary here are numbers which are, in several thousands, and your experience, year of experience, if you captured it in years, are small integers, right? So the dynamic range of these two columns is vastly different, and that is never a good idea when you are running your models from a numerical perspective, because at the end of the day, you remember, you're going to be doing some numerical techniques to optimize and so on and so forth, and therefore it is a good idea if the numerical values of all your features lie roughly in the same dynamic range. Okay, so the magnitude of the numbers are roughly similar. How would you potentially do that? You could potentially do that by perhaps capturing, the experience in months, right? Months. So this could go from, let's say, 0 to 100 typically, and then the salary you could probably capture in terms of thousands, for example. Okay, so units of thousands, in terms of thousands of rupees. So this would go from maybe, let's say, 10,000 rupees, 90,000 rupees. These two guys have a very high salary, but you're sort of bringing the magnitudes closer to each other. Similarly, for the marks and so on, you need to make sure that the features are scaled so that the numerical quantities are, roughly in the same order of magnitude. That's what I'm talking about, because that's going to help your performance of the numerical algorithms that you finally apply for your optimizations. Inconsistent formats. Now again, these are things that you would see in practice. This has been, like I said, here somebody, the guy who was gathering data, put a unit over here, although he was not supposed to. For some candidates, the marks were captured as a percentage. For some, they were captured in absolute terms. So the total marks. So you have to, of course, look at, this. You have to look at this and ensure that your formats across all the rows for each feature are the same. You cannot go about having some people tabulated as percentages and some people tabulated as total marks. So that is what inconsistent formats means, and this is something that needs to be clearly addressed. Managing outliers. Sometimes what happens is that when you gather data, you make mistakes, or there could be measurement errors, and some of the numbers are, way off. So for example, perhaps these salaries right here are way off from, what you would expect salaries to be for people with this sort of experience. Now, what outliers end up doing is, we've been talking about the square distance everywhere, and therefore outliers have a disproportionate influence on the performance of your optimization algorithms, right? So if you are going to look at points, if your points were, all the points were in some range and one point was far away, if you're working with distances, square distances in particular, to do any optimization, this distance would have an overwhelming impact. It would have a disproportionate impact. It was a wrong reading, and such a wrong reading is having a disproportionate impact on your result, and that is something that you don't want. And therefore, removal of outliers, you basically just remove them. Removal of outliers is something that you may want to do upfront with your data so that the performance of your model is not messed up. Finally, mapping categorical features. Okay, so not all features are numerical when you gather them. So I have thrown an attribute called attitude over here, and the person who did like a brief 5-minute interview with each of these candidates put in a one word over here. So it's a friendly, nasty, okay, whatever. And needy, I don't know what that means, but somebody thought that a candidate was needy and therefore he may be more sincere. I don't know what that meant. But the attitude, so somebody captured the attitude, and obviously if you're running optimizations or numerical techniques, such descriptors are not going to work, and you may need to come up with a scale. You may need to come up with a numerical scale where you put, where you map these non-numerical quantities to numerical quantities that make sense from your point of view. So friendly may be over here, and nasty may be over here, okay may be over here, and so on and so forth, and you will have to assign numerical quantities to these guys, right? So that is what mapping categorical features means, and it is something that you may have to do on your data. So all of these are fairly straightforward. These are fairly intuitive. These are something that you would imagine you would need to do. The point I'm making is this is something that you should pay attention to before you start using your data. That is what this slide is all about. Now I want to caution you. Data pre-processing does not mean manufacturing data. Sure, we did an interpolation over here, but it was not, you did not pluck data out of thin air and put it in a missing cell. So you have to ensure that whatever pre-processing you do does not impact the genuineness of the data. You don't want to do something that you pull out of thin air, and that does not reflect the reality of what the data captured was. So you have to be careful about that, but this is what data pre-processing is. Yeah, like I said, you have to take care not to make things worse. You have to make sure that your data pre-processing does not actually mess up your data. Okay, now let's talk about feature selection. Okay, feature selection is the data pre-processing was the first aspect. Feature selection is the next aspect of feature engineering. And as the word suggests, feature selection, it's it's easy to understand what feature selection is. So you have collected data regarding several features. You have collected data on several independent variables, and you sometimes end up selecting only some of them for your model. So you discard some of the features, you discard some of the columns of your data and work only with the remaining columns. That is what feature selection means, as the word suggests. Okay, so again taking the example over here, you may want to not use some of these columns for your model, for your go no go model. Ignore some features. This is what I'm talking about. Ignore some features and focus only on others, right? So you do not want some of the features which are less important to affect your answer, and therefore you ignore some of the features while you focus only on the others. Again, saying the same thing, remove redundancy or less impactful features. Now, many times, visually, which features may be impactful, which features may not be impactful. For example, if you are shortlisting candidates for a job, clearly the feature of ID, this is just an identifier for the candidate, and this does not impact his or her capability to do the job. So you may want to just simply drop this column. Perhaps you also decide that the experience, the job experience and the salary is more important. Maybe graduation marks are not all that important, and therefore you decide to drop this column entirely from your model and just use experience and salary as the features that your model is going to work with. So that is an example of feature selection. Sometimes you can just sort of do it visually because you as the domain expert knows what's going to be impactful and what's not going to be impactful. Now, in some cases you could do it visually. Some cases you could sort of use your domain expertise and do it just by looking at what the features are. But there are also techniques to do it in a more systematic fashion. And the techniques, there are two particularly common techniques called forward selection and backward elimination. Okay, so forward selection is a mechanism to identify the features to retain. Backward elimination is also a mechanism to determine the features of the total features, which features you are going to retain. And their approach to doing so is mathematical, and it's, you know, sort of opposites of each other, but both of them are actually doing the same thing. Now, how does forward selection work? Well, you do what you would normally do. You break up your training data into the training set and a validation set, and you begin with each, you begin with each individual feature and determine the single feature that gives you the best accuracy on your validation set. Okay, so you identify the first feature, the feature that is most impactful. And the most impactful, how do you determine which feature is most impactful? You let's say you begin with marks, and you find you've broken your data set into, let me clean this up. You've broken your data set into a training set and a validation set. So these, you also had, this was binary classification. So you also had your outputs. Let's say you took this guy, you didn't take this guy, you didn't take this guy. This guy was nasty, but you took him for some reason, and so on and so forth, right? So these are the outputs, and you've broken this set into a, this is your training, this is going to be your training data, and this is going to be your validation data. And what you're going to do is you're going to use just one feature. Okay, you're going to use just one feature, ignore all other features, train your model using just this one feature on your training data, and see how well it does on the validation data. And you do the same exercise for every single feature, taking one feature at a time. And the feature for which your model performs best on the validation data, you put it as the first feature in the list of features that you want to retain. After having done that, you start taking pairs. Okay, pairs, but with one of the two features being what you have already selected. So xi is going to stay, xj is what you want to determine. So is the combination, let's say the marks was the feature that worked very well for you first. So you are going to retain marks, and then you are going to see which combination of two features. So is it going to be marks and experience? Is it going to be marks and salary? Is it going to be marks and attitude? That give you the best results on validation data. So what you do is, again, you sort of do brute force. You use marks and experience, train your model on this training data, see its performance on validation. Then you use marks and salary, do training on training data, look at the performance on validation, and so on. Now you have here already selected marks, so you're not going to try out combinations like experience and salary. Now you may say that they may actually give you a better answer, but that is not how the way forward selection works. Forward selection says that if you have already chosen marks as your first feature, your subsequent combinations have to include marks and something else. Okay, so that is how you determine xj. And then you take three. So let us say your first was marks, second feature was salary. So then these two are going to be in, and then you look at the third one. We will look at the third feature which gives you the best results on your validation set, and that is how you go. And let us say you wanted to work with a maximum of k features. This is how you go to k features. This is known as forward selection. It's a brute force method, and it leaves the question open that is this xi xj the best two tuple, or is there an xj xk that can provide better results than xi xj? But that is not, that is the limitation of forward selection. This is how forward selection works. What is backward elimination? Backward elimination is also pretty much, it works in the other way. You begin by taking all the features at your disposal. Let us say you had d dimensions. That means d independent variables, d features at your disposal. What you are going to do is you see what the accuracy of your model is if you use this training data and validation. You built your model with all of these features. Your model with all of these features, and then you start eliminating features one by one. So first you drop this. And see how well your model performs if you use these three features. Okay. And you essentially end up dropping the feature that that you drop the feature that does not cause a disproportionate impact on the performance on the validation set. So for example, if on the overall validation, if on the overall if on the overall features, let's say your accuracy on the validation set was 72, when you dropped marks it became 71, when you dropped experience it became 63, when you dropped salary it became 68, and so on and so forth. Which one are you going to drop, right? Which one are you going to drop? You are going to drop, you're going to make sure that the drop in your accuracy is not very high. Now marks did not cause a significant drop in your accuracy, and therefore this feature you will no longer use, right? I'll repeat this. Deleting marks did not cause significant damage to the performance of your model, and therefore this feature can be discarded. Okay. On the other hand, when you dropped this feature, your model performance went down drastically, and therefore you know that this is an important feature, and therefore you are not going to drop it, right? So you ended up with D-1 features because you dropped the one that was least impactful, and you kept doing that. You kept dropping more and more features until you were left with only K features, right? So this is the way backward elimination works. Again, it's a brute force mechanism. It's a brute force mechanism, and the same drawback that I mentioned for forward selection. What if by dropping a particular combination of two, you end up, messing yourselves up? That can happen. That possibility remains open. Typically does not happen in practice, but that is how backward elimination works. It's a drawback of backward elimination. Okay, so these are the two techniques for doing feature selection. Okay. The next idea that we are going to work on is feature extraction. Okay, feature extraction is different from selection. Feature selection, you are selecting features as they are. In feature extraction, you are going to do something different. And what is it? You are going to create new features. You are going to create new features from existing features. And you imagine that these new features could be more meaningful for your model. Okay, so feature extraction actually pertains to extracting newer features from your existing features. And how you go about doing it is the question that we are going to answer in this lecture. Now, remember, features are often captured based on the ability to measure parameters, right? You have certain measuring instruments, you have certain you have certain features that can be easily captured, and the process of capturing features often follows a path whereby you capture the values for features that are easy to capture, right? And they may not be the best features for our purpose or for our model to get to the results that we want. But this is the reason why feature extraction is important, because what is captured is typically what is easy to capture, and that may not be the best thing to use for your model. Okay, so that is the purpose why feature extraction is something that is done. Here are some examples. We already talked about, I showed you a figure where distance from the center instead of using XY coordinates was a better way to go about your model. However, while you were measuring, the person who was measuring could measure only X and Y coordinates, and therefore X and Y was what was captured. However, for your model, the distance from the center was a better feature to use, and you can go from here to here. You can find the distance from the center using X and Y, but it is a feature that has to be extracted from what you have, right? Similarly, let us say you were trying to build a model that predicted the prices of homes, and you are capturing the address, right? Address or pin code or whatever. But what is more important when looking at prices at homes is the sort of the neighborhood it is. Is it a low crime neighborhood, etc., etc. And therefore the neighborhood may be a better parameter to use while predicting prices of homes, and the neighborhood can be ascertained from the address itself. Here are more examples. if you're doing some sort of motion detection, you are capturing images, you may want to extract edges from the images from your video while you're doing motion detection. Similarly, if you were doing with you are dealing with PDF files, depending upon what you are doing, you may want to use word counts. And if you are dealing with audio, you may want to look at frequencies rather than the raw audio itself. So these are all examples of feature extraction. You come up with newer features from the features that you have at your disposal, from the features that were measured. Okay. The PCA, the Principal Component Analysis Technique, and the LDA technique, the Linear Discriminant Analysis Technique, are two mathematical techniques that do feature extraction. And these two techniques are the primary focus of today's session. Okay. PCA, Principal Component Analysis, and LDA, both are feature extraction techniques. And these are going to take up the rest of this lecture. Okay, now before I jump into what LDA and PDA are, one question remains unanswered. Why do we do feature selection or feature extraction in the first place, right? I mean, generally your attitude would be more the merrier, right? I mean, that would be sort of an innocent way of approaching any problem. Gather as much data as possible, let your model run on it. And if you can build very, very complicated models, maybe that may work. I mean, feature extraction and selection may actually become a part of the model itself. But for the basic models that we are covering in this course, feature selection and feature extraction is seen as distinct from the model itself. Okay, so the question remains, why do we do feature selection? Why do we do feature extraction? And why don't we just say more the merrier? Why is our answer not better when we have more information at our disposal vis-a-vis actually, reducing the data that we use in our model? Okay. The phrase used for this is dimensionality reduction. And what dimensionality reduction says is that you would usually like fewer variables or features in your problem. Why is that? Why do you want to indulge in dimensionality reduction? Okay, the first reason is of course obvious, lesser computation. If you have fewer features, your model is that, the model has to deal with that much less data, and that means lesser computation. And lesser computation may be a governing factor in several cases. Okay. More features means more complex models, which can give rise to overfitting or poor generalization. Now, we've spent a lot of time talking about the theory of learning. And one of the things that the theory of learning taught us is that more complex the model, for the same amount of data, a more complex model leads to overfitting, right? It ends up doing very well on training data and it does not generalize very well. It does badly on out of sample data, right? On the test data. So we know this. This is what the theory of learning has taught us. And more features would clearly mean more complex models. So therefore, you do not, if you want to avoid the trap of overfitting and poor generalization, you are better off using fewer features and creating slightly lesser complex models. Okay. So this is the other reason, most important, why you would want to do feature selection in the first place, or why you would want to work with a fewer number of features. Okay, the third reason is that in higher dimensions, data becomes sparse and distances become less informative. Okay, so distances start giving less and less information. Remember, the idea of distance is central to any optimization algorithm. You can define the distance in the way you choose, but as you go into higher and higher dimensions, the data becomes sparse, right? So hard to visualize in dimensions more than 3, but you could have in 2 dimensions or in 1 dimension, the data could be packed close to each other. And as you add 2, 3, you go to higher and higher dimensions, this data the data points would be farther and farther from each other, right? Because you have more dimensions. And it can also sort of mess up the idea of distance in a way that may lead to poor results. What I mean is that, let us say two data points which are actually supposed to be close to each other are indeed close to each other in, let's say, two dimensions. But when you added a third dimension, in the third dimension, it was the 2 points were further away from each other. That dimension was not of much use anyway, but the distance in the third dimension overwhelmingly messed up the overall distance between the 2 points, and therefore your algorithm started, or your model started, behaving poorly. Now I said 2 and 3 dimensions, but imagine a case where you have 500 dimensions. Let's say, I mean, taking extreme examples to make a point. In 499 dimensions, your two data points were close to each other. In one dimension, they were far off from each other. That was a spurious sort of a feature in any case. But you know how Euclidean distances work. That one distance in that one dimension is entirely going to mess up the distance between those 2 points, right? And the points that were supposed to be close to each other are now going to, have massive distance between them, and that is going to impact your model performance. That is what I mean by saying that data becomes sparse and distances become less informative. Okay, so therefore you want to focus on fewer features that you really need. Of course, there are other reasons. You want to remove noisy and redundant features. Of course, some of the noisy redundant features would make the data sparse, so on and so forth. So these are, sort of related to each other, but you want to remove noisy and redundant features. And finally, you prefer to keep independent features. Okay, independent features meaning features that don't depend on each other. Remember, very early in the day when we were talking about linear classification, we talked about this, why it is important to have independent features. Basically, the performance of models improves, the impact of noise is lesser, and your understanding of the problem, it's easier to understand a problem when features are independent of each other, uncorrelated with each other. That's why you draw your x and y axis orthogonal to each other, right? I mean, you could also have a coordinate system with two axes like these, and every point would have coordinates. But why do you keep it this way? Because it's easier to understand, because x and y are clearly orthogonal to each other. So that is the same philosophy, that's the same logic why you would want to use independent or uncorrelated features. To summarize, therefore, fewer variables can therefore enhance model performance. Fewer variables can therefore enhance model performance. The logic of more the merrier does not work. You may actually want to work with fewer variables that make most sense. Okay? That is why you do feature selection and feature extraction. Finally, I hinted at this, you could also do feature transformation within the model itself, and kernels are an example of that. Kernels exactly do the opposite. Kernels transform data into higher dimensions to meet our purpose. So you can imagine that if you added a few more dimensions, there could be problems. I'm saying that you could imagine. I'm not telling you right now what these examples are. We are going to cover an example in the next lecture. But you can imagine that by adding higher dimensions, you could actually achieve class separation and so on and so forth. And therefore, you may want to include in your model the ability to do that by adding more and more features. And that process is known as applying kernels. I'm going to discuss this very briefly in this lecture, but that is what kernels are, and we'll discuss these in great detail in the next lecture when we talk about support vector machines. Okay, so this I just mentioned here for completeness. Okay, now studying PCA or LDA, requires us to know something about eigenvalues and eigenvectors, and I am going to spend a minute talking about what these are. Some of you probably already know what eigenvalues and eigenvectors are, but let's go over this fairly quickly. Okay, so for a matrix is also called a linear transformation. Eigenvalues lambda and eigenvectors v are quantities that satisfy the matrix equation AV equal to lambda v. In other words, if you apply the transformation A to a vector v, you end up with a multiple of the same vector v, and this multiple could be, positive or negative. So vectors that satisfy this equation for a particular transformation are called its eigenvectors, and the corresponding value of lambda is called its eigenvalue. So that is the definition of eigenvectors and eigenvalues. Now clearly this equation itself shows that this equation can only apply if A is a square matrix, right? So A has to be an m by m matrix where m could be any number. This equation cannot be satisfied if A is not a square matrix. As you can see, the number of columns of A have to be equal to the number of rows of V, and the number of rows of A also have to be equal to the number of rows of V, and therefore A is a square matrix. For each eigenvalue lambda, there is an eigenvector V and vice versa. Okay, so you will have, for any matrix A, you will have several pairs of eigenvalues and corresponding eigenvectors. Okay, so lambda and V occur as pairs for any matrix A. There are m such pairs in general, and they uniquely define A. So in general, a matrix of size m by m will have m eigenvalues and correspondingly m eigenvectors, and they in turn can uniquely be used to uniquely define A. The vectors V are also called the core axes or the principal directions of A. These are, this is some more terminology in case you run into it. Core axis or principal directions are basically the eigenvectors of matrix A. And finally, the eigenvectors of a symmetric matrix are orthogonal. So everybody knows what a symmetric matrix is. A symmetric matrix is where a term Aij is equal to Abi, right? So this value is equal to this value, this value is equal to this value, this is equal to this, and so on and so forth. So this is a symmetric matrix, and if A is symmetric, then its eigenvectors are orthogonal to each other. Okay, I want to show you graphically what eigenvectors and eigenvectors basically look like. So let us say you have a matrix A, which is a linear transformation, and by linear transformation I mean if you multiply any A with any vector with a value xy, right? Xy is a point, and if you multiply this by matrix A, you get a transformation that maps this point to a different point in the two-dimensional space. So for example, if you multiply any vector V with the matrix A, you will get another vector W, which will basically have, the new coordinates, the transformed coordinates x dash and y dash, starting with x and y. So that is what it means to say that A is a linear transformation, because it maps every point to some another point, and that is why we say that, it transforms the input space into an output space. Now, this is a pictorial view of what, a transformation would typically do. Now, I've sort of taken this matrix A as an example to illustrate the point, and the reason why I've chosen these numbers here will become clear in a moment. But what this matrix is going to do, it's going to map this input space to an output space that looks like this. So for example, the vector I, which was 1, 0, gets mapped somewhere over here. So this would be something like, 1.8 and minus 0.2, something like that, right? So that is this point. So I got mapped over here. J, which was 0, 1, got twisted and got mapped to this point. This is probably plus 1.1, sorry, the x coordinate would be negative, maybe minus 0.5, and the y coordinate is, let's say, 1.1. So the point 0, 1 in the input space got mapped to this new point in the output space. So similarly, I mean, you can look at this figure, pause the video for a moment, and you will see what is being done over here. This basically shows these gray parallelograms basically show how the input squares got mapped to this, grid of parallelograms after application of this transformation A. Right? So this is what a linear transformation would typically do. Now, what you will notice is that every point has moved, right? So for example, 0.10 got mapped over here, 0.01 went over here. So every point in the input space sort of got mapped to a different point in a different direction and so on. However, there are two directions in which even after the transformations, the points stayed in the same direction. One of those is, for example, the point 1, 2. Okay, so this point of the input space, this was 1, 2. Even after application of the transformation, it stayed at the same place. Okay, it stayed at the same place, as you can see. So the transformation, the matrix transformation, did nothing to move the point to another location. It stayed where it was. In more general terms, it stayed along the same direction. Okay, so if the eigenvalue is 1, it will stay exactly at the same place. If the eigenvalue is, let's say, positive, larger than 1, it will get transformed to some another point, but along the same direction. So it could go over here. If the eigenvalue is less than 1, it will go somewhere over here. If it is negative, it would go over here. But the bottom line is that there are two axes. This one and this one, where points that were originally on these axes continue to be on those same axes, right? With possibly a scaling or a change of direction. And in other words, the scaling could be positive or negative, but they stay on the same axis. So these are the eigenvectors. These are the eigenvectors of this particular matrix A. The second eigenvector is, if you let me see what these eigenvectors are. The first eigenvector is 1, 2, which I just showed you. And the second eigenvector is 3, -1. So if you look at the point 3, -1, right? The point 3, -1, even after the transformation, has stayed on the same line. Okay, it has stayed on the same vector. Okay, so that is where has the point 3, -1 gone? The point 3, -1 has gone here. Okay, this is where it is, and it is in the same direction. Like I said, it could scale. It will go from here to here, but it remains on the same vector. So this is one eigenvector, this is the other eigenvector, and the amount of scaling in those directions are the corresponding eigenvalues. So this is how eigenvalues and eigenvectors are related to the transformation matrix. They are essentially the directions on which there is no impact except for a positive or negative scaling, and and therefore they are characteristics of the linear transformation. So I used a tool available online to show you this graphic. That is what eigenvectors and eigenvalues really are. Okay, so for these vectors or any multiple of these vectors, they would satisfy this equation for some lambda. So not just this vector, it could be instead of 1, 2, you could have 2, 4 or 3, 6. Instead of this, you could have 9, -3. So essentially anything along these directions would remain in the same direction with a multiplier lambda. Okay, let's move on. With that background, I think it is now time to look at principal component analysis. The question that the PCA tries to answer is this: if I am allowed to keep only a few features, and you know why we do this, we want to basically minimize the complexity of the model. So if I am allowed to keep only a few features, which features would you preserve so that the maximum amount of information is retained. How do I achieve dimensionality reduction with minimal loss of information? In other words, the question I am asking is that if I am permitted to keep only a few features, if I am allowed to keep only a few features, which features would those be? Of course, I would want to retain the features that retain maximum information about your input data. Now we are going to formalize what that means. But essentially, you do not want to keep, just because you want to keep few features, you do not want to keep some features that are not really useful or which do not give you insights into the data that you want. You want to keep the features that give you maximum possible information or result in a minimum loss of information by retaining just those few features, right? So that is the question that the principal component analysis attempts to answer. If I am allowed to keep only a few features, which features would preserve the maximum amount of information? How do I achieve dimensionality reduction with minimum information loss? Okay. PCA is a technique for feature extraction for unsupervised learning. Now, you know what unsupervised learning is. There are no input-output pairs. You are just given an input. And typically in unsupervised learning, you are trying to do things like clustering and so on and so forth. We looked at the k-means clustering. And that's an example of what you would do in unsupervised learning. And PCA is a technique. PCA, principal component analysis, is a technique for feature extraction for unsupervised learning. So it answers this above question in the context of unsupervised learning. Okay. So what is it that principal component analysis is going to do? What principal component analysis is going to do is it's going to create new features. It's like I said, a feature extraction technique. So you're going to create new features from existing features that will be more useful for our purpose, such as clustering, which is an example of unsupervised learning, or any other purposes that have to do with unsupervised learning. Now, again, I repeat myself, these new features may not be recordable or visible features. They are somehow obtained from the features that were observed. So, what are some of the applications of unsupervised learning where PCA could come in handy? Clustering, like I said, k-means. K-means is something we have studied. Clustering is a very important application of unsupervised learning. Outlier detection. We said early on that we want to identify outliers and perhaps eliminate them from our training data, and PCA can come in handy when you are trying to do outlier detection. And finally, estimating distribution. I mean, you may want to estimate the distribution of the data in terms of different features from the one that you have recorded. So these are applications of unsupervised learning where PCA could come in handy. Okay. Now let us talk. I said 3 examples of unsupervised clustering. Analysis was one. So let us ask specifically about clustering. Specifically about clustering, what sort of features would you like to use? I mean, if you were told to use only a few features, what are the characteristics of those features that you would like to retain, right? So what are the features that you would like to retain? What would be their characteristic that is important to you? The answer is that you would like features that demonstrate maximal separation within data, because this maximizes the information conveyed. Okay, so you want to retain features where there is maximum separation within the data, where the data is not, along those features, the data is not tightly clustered together, but has a good degree of separation. Those are the features that you would like to maintain, because that sort of maximum separation maximizes the information conveyed to you by the data. Now, the word information is, it's a technical term. It's not like a colloquial word. So what do I mean by saying that it maximizes the information conveyed? Well, if you've not heard of entropy, ignore what I'm going to say. But for those who have heard of entropy, measure of entropy is bits. So you measure information in terms of bits. And let us say if you had maximal separation, if you had a bigger dynamic range, you would need more bits to specify where a particular point actually was. In other words, if you are going to be using more bits to convey the location of a particular point, you are conveying more information. If you just need fewer bits to convey the location of a particular point, then the information being conveyed is less. So that's the information theoretic way of looking at it. Maximal separation also maximizes the information that the data is conveying to you. And clearly, even from an information theoretic perspective, if you are going to use fewer features, you want to retain those few features that convey to you the maximum information, and therefore you want those features that demonstrate maximal separation of data. Okay, great. This is what you want to do in clustering. Example, loan approval on 2 parameters. Let's say, okay, so you are trying to, you're sitting in some financial institution approving loans of applicants, and you are looking at 2 parameters, salary and house size. And let's say you are sitting in a place like Mumbai, Bombay, right? Now, the salary is likely to give you more information. Salary is going to likely to give you more information, since house sizes, especially in a place like Bombay, are likely to be in a tight range. I mean, typically the guy who applies to you for a housing loan is typically already staying in a house which has perhaps 700, 800,000 square feet, right? Although the salary ranges could vary from anything from 20, 30,000 to 3, 4 lakhs. So clearly the separation of the data in terms of salary is much higher than the separation in terms of house size, and therefore if you had to maintain only one out of these parameters, you would probably base your decisions based on salary rather than the house size. So what am I trying to convey with this example? All I am trying to say is that if you had to make a choice, you would typically go with a parameter that has maximal separation of data. Okay, because that gives you more insight into the data. Okay. Here is another example. Another example. Let's say you are, you have gone to watch a game of football, and let's say you are the chief guest. Okay. You are going to watch the game of football. You are the chief guest. Typically, where would you be sitting? Okay. Think about it for a moment. If you are watching a football match, which is the place where a chief guest would be sitting, right? You would probably be sitting somewhere over here, okay, along this larger edge of the football field, right? I have never seen a football ground where the chief guest box is like over here or over here. I have never seen one. The chief guest box is always over here, right? Why is that? Why is that? Because if you were sitting here, you would be able to determine the maximum separation of the players, right? This is the axis along which you are able to see maximal separation of the players. Over here, the players would be packed in a smaller area. Now, I don't know if people who, what the people who were thinking when people build football stadiums, but in some way or the other they are exactly thinking about this colloquially speaking gives a better view of the football field. In more technical language, it is giving you maximal separation among the players who are on the field at that time, and therefore it is conveying maximum information to the chief guest. Okay, so this is another example of where you would like to retain, if you were to see along only one dimension, like forget for the moment that a person has 2 eyes and therefore he can make out the depth and so on and so forth. Forget all that. If you are a chief guest with just 1 eye, you would like to sit over here because that is the direction along which you would see maximal separation of players. Okay, so that is what I mean. Trying to give you an intuition into why you want to choose features or directions that convey maximal information. Okay, coming back to a diagram like this, if you had x-axis and y-axis, if these were 2 features, x1 and x2, if x1 and x2 were your 2 features and this was your data, unsupervised data, so there is no labeling, what you would like to do is if you were to choose only one of these two, if you were to choose only one feature, if you are allowed to look at this data along only one direction, you would neither choose x1, you would not choose x2, you would probably choose a direction like this, x new, because the separation along this direction is the most. Okay, for this particular example that I have shown. Let me describe to you this once again in slightly more detail. Now, what is the separation along feature 1? It is approximately this one. Okay, this thing. This is the separation along feature x1. What is the separation along feature x2? Separation along feature x2 is this. It's clearly less than x1. What is the separation along this new direction x new? It is this, right? And as you can see, the separation along x new is more than the separation along x1, more than the separation along x2, and therefore if you were told that you get only one direction along which you are allowed to observe the separation of the points, you would probably want to do it along this direction x new, which is neither x1 nor x2. Okay? So this forms the basis of PCA, or Principal Component Analysis. What we are going to be spending time on is essentially determining this direction x new for a given set of points. That's the long and short of it. Now let us look at another application of another unsupervised learning application, outlier detection. In this case, you are actually going to do the opposite. You are going to look for minimal separation of data, because that is what is going to allow you to identify outliers, right? So the information conveyed over all the points is less, but the key information that you are looking for, the outliers, are going to be captured in a better manner over here. And this is the direction along which the separation of the points, is minimal, and therefore if there was an outlier, you would be able to capture it pretty well. So if you were doing outlier detection, you would actually be looking for an axis that has minimal separation of data along it, right? So I just wanted to, this whole outlier detection business and minimal separation is never discussed in the context of PCA. Okay, but it is important to understand both ways. I mean, when is maximum separation useful? It is useful when you're doing clustering or you want a maximal information over all points, right? But if you're looking for that one specific point which is an outlier, you are probably better off looking along a direction where all the points are clustered together, because if everything is clustered together, an outlier can be easily captured, right? So you may even want, in addition to finding a direction that shows maximal separation, you may also want to find directions that show minimal separation overall. Okay. I wanted to put this out here. Like I said, this is not typically mentioned when people discuss PCA, but it's important to understand what happens along directions that have minimal separation of data. Those are good to look at outliers if you want to capture outliers. Okay. So now coming to PCA, I'm only going to talk about maximal separation, because by far clustering and analysis is a much more common application compared to detecting outliers. Detecting outliers, you sort of in pre-processing, you detect the outliers and you're done with it. But if you're going to be running models subsequently, you are going to look for maximal separation, which is typically done for clustering and so on and so forth. And therefore, for the remainder of the lecture, when I talk about PCA, I am going to be talking about maximal separation of data. Okay. So what is the mathematical objective in PCA? You want to extract features, you want to determine features such that number one, they demonstrate maximal. Minimal, like I said, I'm going to ignore for a while, but the mathematical theory will also give you directions of minimal separation. That is what I'm saying. By far the most common applications look for maximal separation. So extract features that they demonstrate maximal separation are independent. Remember, we have all been harping on this point. We want our features to be independent of each other because they give us better insights, etc. So why not add that to our wish list and say that we want directions that demonstrate maximal separation. We want directions that are independent of each other. And of course, they are fewer than what you began with, because that was the whole objective. You always said that you want to reduce the number of features that you were dealing with. So the mathematical objective of the PCA algorithm is going to be that you want to extract features that demonstrate maximal separation, are independent of each other, and of course their number is fewer than what you began with. Okay, now let us formalize in terms of equations our objective. Okay, we had an objective, we said we want to maximize separation, blah blah blah. Now if we are going to optimize that, if you are going to sort of do some math on it, you need to define these quantities in mathematical terms. So the word separation is something that we have used extensively, right? So let us define what would be a good measure of separation. Now if these were our points, let us say our x mean, the mean was over here. This need not be an actual point. This is just the mean along the direction x1 of these points. And this is the separation, right? Now, just the dynamic range of these points, I used the word earlier, but that is not a very good measure of the separation of data. Okay, and the reason for that is that you could have outliers. So for example, if there's one outlier over here and one outlier over here, this would be the dynamic range of your data. And most of your data is clustered over here. So you don't want a situation where outliers are disproportionately messing up your math. And therefore this whole dynamic range business, max minus min, is not a good measure for separation. Okay, a better measure for separation is the variance. Okay, it's a variance along that axis, and variance along an axis as a measure of spread or separation is a much better measure, because variance is measured over all points. You know what variance is. Basically the coordinate of that point minus the mean square, right? So the variance of the points along this axis x1. So for all of these points you get the x1 coordinate. This is how you get the x1 coordinate, and you take the variance. Okay, so you take the variance of the x1 coordinate of all the data points over n data points, and we use that as a measure of the spread or separation rather than the entire dynamic range. And clearly variance is one metric. It's a good metric. It's a good metric because it is, it is not overly influenced by outliers, and it captures the significance of each of these points. It penalizes the further points a little bit more, but it is a measure that pretty much captures the physical aspect that we are trying to look at, the separation. So variance as a measure of spread or separation is something that we are going to go with. What is the variance? Like I said, summation from 1 to n over n points, x along the x1 direction. My notation is going to be that I are the points. I'm going to keep that as a superscript. So I goes from 1 to n. x1 is the axis. x1 is the axis or the feature that we are talking about. x1, this should have been x1 mean. x1 mean is the mean along the x1 direction. So the variance along the x1 direction, which I am calling sigma 1 square, is 1 over n summation from 1 to n over I going from 1 to n, x superscript I1 minus x1 mean, the whole square. This is the variance. So this is the variance of the points along the x1 direction, along the x1 axis, along the x1 direction. And because, okay, without loss of generality, I am going to assume centered data around the origin. The spread does not depend upon the mean, right? So I can move these points along the x1 axis so that the mean is 0. Their mean is 0. And if my mean is 0, I can do that without loss of generality. W log means without loss of generality. We can assume that the data is centered around the origin, which means that my variance along that axis is simply 1 over n summation I going from 1 to n of xi along the direction 1 square. So this is what my variance along that axis is. Fair enough. Okay, now I have been using this implicitly, but for abundant clarity, projection of a point along the direction is the coordinate along that direction. You know that, right? And what do I mean? Graphically speaking, let us say I have a direction Z. Okay, this is a direction Z. Z is a unit vector along the direction, along this direction, unit vector along this direction. And what is the coordinate of this particular data point along this unit vector? It's the projection. It is this value, right? So you drop a perpendicular from this point to the unit vector Z, and where the perpendicular intersects, this is the projection of the point along this direction, and it is the coordinate of this point along this direction, right? It is the coordinate of this point along this direction is simply obtained by projecting this point over here, and this is the coordinate of this point along this direction, right? And how is that obtained? That is simply obtained by taking the dot product of that point with the unit vector in that direction. So the vector pointing, I'll draw this a little bit more carefully. So this is the vector defined by this point. If you take the dot product of this vector with the unit vector Z, you will get this quantity. The dot vector is, the dot product gives you a number, a scalar, and this quantity, which is the scalar, is found by taking the dot product of this with this unit vector Z. We all know this from coordinate geometry. So Zi, the projection of the ith point along the Z direction, is found by taking the dot product of xi, the vector of coordinates of the point I, with the unit vector Z, and it is also written as x transpose Z, right? So very careful. What is xi? Xi for the ith point is this vector. Xi, the vector xi is for ith point. You take the ith point, right? There are n points out of which you take the ith point, and this would be x because it's ith point. This is I1. So the coordinate of the ith point along direction 1, the coordinate of ith point along direction 2, the coordinate of the ith point along dimension 3, etc., 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 right? And let's assume you have total of d dimensions. So this would be what your vector is, right? Okay, so you take the dot product of this vector, you take the dot product of this vector with the unit vector Z, and that would be the projection of that point along the direction Z. Okay, this is again basic coordinate geometry, important to understand. Expanded, I just showed you what it was. This is x, xi1, xi2. So this one, this two, etc. are the directions, the original directions, right? The original coordinate axis. And I am talking about the ith point over here, right? Okay. And the z is of course z1, z2, z3, etc., etc., right? All the way to zd. This also goes to xdi. So you take the dot product of these two vectors, z1, z2, z3. This is a fixed unit vector. It will have d coordinates because your original space had d dimensions, and you take the dot product of these two. Now variance along the direction z, is therefore, you know, if I wanted to find, if I took the projections of all of these points along this direction, right? So these would be the numbers, and the variance of those numbers along that direction z would be 1 over n summation zi square, right? Because zi is the projection of xi along z, right? So because my data is centered, it's also centered around z. If I have centered it along all axes to begin with, it's also centered around z, and therefore this is going to be my variance along the direction z, right? So this is zi right here for the ith point, and I am going to sum this from 1 to n. This is the variance along the direction z. Okay. what do we want to do? We want to essentially choose the direction z such that this is maximized, right? So whenever I show this, you may think I'm looking at the spread. I'm not. I'm looking at the variance. But you want to choose the direction z. You want to optimize over z. You want to select z such that the variance of your input data along that direction is maximized. That is what you want to achieve. Okay. Now that we know what the goal is, you want to find the direction z such that the variance along it is maximized. You know what the variance along any particular direction z is. Now what remains is the math, right? That's what we are going to do. So to restate, the variance along any direction z is given by this equation, where zi is the projection of the ith point along that particular z-axis, and of course your summation, you're running the summation over all the points in your training data. I'm going to just put this over here so that you don't forget. D is the original number of dimensions, Z is the unit vector in D dimensions. Of course, it's in D dimensions. Z is the unit vector along any particular direction. We are going to find the best direction Z, and N is the number of training points. Okay. So I'm going to leave this here in the corner if you are confused at any point in time. There should be no room for confusion over here. I have written the variance along the direction Z instead of using summation, I have written this in the vector matrix notation. Okay, I have written this in the vector matrix notation, and this step going from here to here is the most important step in understanding the math behind PCA, because after this point everything is a vector matrix operation and it will be very simple. But you have to convince yourselves that this is exactly this. Okay, I told you what Z was. I told you what Z is. Z is basically a vector of dimension D. D is the number of dimensions in your original space. So Z has, Z is a vector that looks like this. It's a unit vector and its components are Z1, Z2, Z3, etc. It's the vector, it's the matrix X, this matrix X, which is what you have to look at. The matrix X is essentially the matrix of your input training data. Okay, so its rows are essentially rows for each particular point. So this is point 1, point 2, point number 3, going all the way to point number n. And each row, for each point, you have basically put the coordinates along the various the original dimensions. So x along x1 axis, along x2 axis, along x3 axis, and along xd axis. Let's say I said d is the number of original dimensions. So to repeat, for point 1, this row, let us say, let me take something else, point 2, this is for point number 2 of your training data. This is the coordinate along the first direction, coordinate along the second direction, coordinate along the third direction, coordinate along the fourth direction. And because this is point 2, the superscript is 2 over here. So this, as you can see, X captures your entire input data for all the n points. These are the coordinates of those points, right? And xz, what would be xz? Xz would be, for any point, it would be the dot product of this vector and this vector. And as we have seen, that is the value of the projection along the z-axis for that particular point, right? So it is the projection along the z direction for that particular point. That would be the dot product of this and this, right? Now, I have the summation of squares. I have captured it as, matrix multiply Z transpose X transpose times XZ. And why does that matter? Why is that true? This is summation of Zi square. How do I get summation of Zi square for a particular point I? I have to calculate this and multiply it by itself. And that is exactly what happens when you do Z transpose X XZ. because xz would be a vector along of the projections of all the points along the z direction, and then when you multiply it by itself, this is the transpose of this. When you multiply it by itself, you are essentially going to multiply the corresponding numbers with themselves, and you are going to get this summation of zi square, right? So convince yourselves that this is exactly what this is, where matrix X is the matrix of your original data. Okay, if you accept this, which you should accept because it is true, the rest, like I said, is simply math. I am going to define a covariance matrix. Which is X transpose X 1 over n times X transpose X. Okay. And once I have defined the covariance matrix, what is X transpose? X transpose is basically the transpose of this matrix, where points are represented by the columns, right? So this is the nth point, right? So I multiply X transpose X and I call it the covariance matrix. And why is it called the covariance matrix? Because it actually captures the covariance, right? The ijth entry of C, the matrix C, this should be bold. The ijth entry of C is simply summation from 1 to n, okay, of xi xj. Okay, so if you multiplied this matrix with this matrix, that is X transpose X, the ijth entry of that matrix, the ijth entry of X transpose X is the summation from xi xj from 1 to n for any point over all the points. So the correlation between the ith dimension and the jth dimension is found by multiplying these two and summing these over 1 to n. Okay, that is what the ijth entry of this matrix is going to be. You can verify this again, like I said, by actually multiplying these matrices and seeing what it is. And this therefore captures the correlation, the covariance between the ith dimension and jth dimension of the input space, and therefore it is called the covariance matrix. Okay, along the diagonal of this matrix is the variance, okay, along a particular axis. Okay, so this is your covariance matrix, and what we want to do now, expressing our objective in mathematical terms, we want to find the direction z in which sigma z square is maximum. In other words, you want to maximize this, right? What sigma z square becomes, if I replace C in this equation, is Z transpose CZ subject to Z transpose Z equal to 1. Why is Z transpose Z equal to 1? Because it's a unit vector. So with subject to the constraint that you are dealing with unit vectors Z or Z, you want to maximize Z transpose CZ, where C is a known matrix. Why is it a known matrix? It is basically it can be computed based on your points, locations of your points, just the coordinates of your points in the original D dimensions. Since those are known to you, since you know the locations of those points, you can calculate the value of C being the covariance matrix. Okay, so this is how you have mathematically captured your intentions. You are saying that you want to maximize Z transpose CZ subject to Z transpose Z being equal to 1. Okay. Now, we have seen earlier how you would solve a constrained optimization problem. It's constrained because you have the constraint Z transpose Z equal to 1 and you want to minimize something. And that is done using what are known as Lagrange multipliers, as we have seen. We saw this when we were doing regularization and so on. So I define the Lagrangian L, which is Z transpose CZ. You want to maximize this subject to this constraint, and maximizing L is okay because this is going to be 0 anyway if Z transpose Z is equal to 1. So this is how you set up the Lagrangian, as we have seen earlier, and keep in mind that C is equal to 1 over n X transpose n. Okay. So how do we optimize? How do we solve the problem using Lagrangian multiplier? You basically find the partial derivative of L with respect to Z. If you do that, you get simply this and you set it equal to 0, right? So L is maximized when the partial derivative of L with respect to Z is equal to 0. And long back we have talked about this. The partial derivative of Z transpose CZ with respect to Z, we have seen this, right? Z transpose CZ. We've seen this long time back. This is simply equal to C plus C transpose times Z, which because C is a symmetric matrix, this is simply 2Z, right? That is 2CZ. That is what I have put over here. And the derivative of this is simply lambda Z, right? And this I have set it equal to 0. And which if you simplify, you get something that looks like this. Okay, something that looks like this. It says that the Z that maximizes the variance is a Z that satisfies this equation CZ equal to lambda Z. And coincidentally, we have seen something like this just a few slides ago. It basically says that Z is an eigenvector of the covariance matrix C. Okay. So, it turns out that Cz equal to lambda Z, okay, Cz equal to lambda Z for the direction Z that maximizes or minimizes the variance, okay, and therefore Z is a eigenvector of the matrix C. Very important, very important. The direction which maximizes or minimizes the variance is an eigenvector of the covariance matrix. Interesting. And what is the variance? If I plug this in for Cz, if I replace Cz by lambda Z, this is what I get. And lo and behold, the variance along that direction Z is simply the eigenvalue, the corresponding eigenvalue. So very, very convenient, very nice. The direction that maximizes the variance is the eigenvector of the covariance matrix, which is known to you, which is basically the matrix of your input points, their coordinates. And the corresponding variance is the corresponding eigenvalue, simply by replacing Cz equal to lambda Z right here. Okay? How nice, how convenient. C is symmetric and therefore eigenvectors are orthogonal and independent. Remember I told you that the eigenvectors of a symmetric matrix are orthogonal. So our second wish list point has also been nicely met. Okay, lo and behold. Now, if you continued the same exercise by adding more constraint, the second eigenvalue has to be orthogonal to first, etc. You can show that the next vector, the next direction which is orthogonal to the first vector, whose variance is the highest, is the second eigenvalue of C. Okay, I'm not going to show that over here. It's simple to prove. But in other words, what we are saying is if you wanted to find a orthogonal set of directions ordered from highest variance to lowest variance, those would be the eigenvectors of the covariance matrix C. Okay, and this is the derivation that just showed that to you. Okay, so what are we saying? We are saying that the eigenvectors of the covariance matrix corresponding to the largest eigenvalues are, they are called the principal components, and those are the directions in which the spread variance is maximized. So the variance is maximized along if you wanted to find the orthogonal directions along which you would have the maximum variance, those would be the eigenvectors corresponding to the largest eigenvalues, and they are also called the principal components. Hence the name principal component analysis. Number 2, the direction corresponding to the minimum eigenvalues minimize the spread or the variance. So remember, in rare cases you want to find outliers using the minimum spread. Well, you do the same exercise and take the eigenvector corresponding to the minimum eigenvalue. Nice. These directions are orthogonal to each other. I said that earlier. And you can decide how many you want to use, thereby reducing the complexity of the problem. So I may say that, the number of initial dimensions was 500. I only want to keep 100 out of those, which are the most important, along which the spread or the variance is maximized. And what I'm going to do is I'm going to find the covariance matrix from the location of my points. I'm going to find its eigenvectors, corresponding eigenvalues. I'm going to order it on the basis of eigenvalues, and you are going to take the eigenvectors corresponding to the top eigenvalues. Now I want to say one thing here, important. I keep saying the largest eigenvalue, largest by magnitude. Okay, largest by magnitude. The question remains, how do you find the eigenvectors and eigenvalues? Well, there are numerical and iterative methods for large sized matrices. For small sized matrices, 2 by 2, 3 by 3, there are closed form solutions. But typically you would be dealing with hundreds of features, and then there are numerical or iterative methods for finding the eigenvalues and eigenvectors of those large matrices. Okay, so this is what principal component analysis is. Principal component analysis, given some data for unsupervised learning, principal component analysis finds those directions along which the spread or the variance as a measure of the spread is the maximum. Okay, and you can take the first few, the first largest eigenvalues by magnitude, take the corresponding eigenvectors and use those as your features for your models. So instead, discard the original features and use those features as the features for your model. One important takeaway is that these new features are linear combinations of the older features. Okay, linear combinations of the older features. And what am I saying? Let me go back. All I'm saying is that if you look at my original example, where was I? Okay, so loan approval on 2 parameters, right? So instead of taking the salary by itself, if I had to choose between salary and house size, I will choose the salary. But if I wanted to invent another single feature that I want to use, it would be a combination of the salary and house size, a linear combination. So take the salary multiplied by something and take house size multiplied by something and add it together, right? So that is a linear combination. So some combination of the salary and house size will give you the maximal separation, and if you wanted to use only one feature, you are better off taking that linear combination of salary and house size. Right now you may say, okay, this was all obvious to me right from the beginning. If I had multiple features and if I had to take only one features, I would take a little bit of this, little bit of that, some more of that, so on and so forth, use my judgment in terms of what's more important, what is less important, and come up with a feature. So then what's the big deal about PCA? What PCA has mathematically told you are the ratios. In what ratio you should take the salary vis-a-vis the house size. That is what PCA has told you, because it has told you what the eigenvectors are, and the eigenvectors actually tell you the ratio or the linear combination in which you are supposed to take the salary and the house size to create this grand one single feature that you can base your loan approval decisions on, right? Okay, excellent. So that is what PCA is all about. Okay, now let us move on to the next technique, which is LDA, which stands for Linear Normal Discriminant Analysis. Let's see what this is. It's a related technique, but of course differs from the PCA. Okay, this is a technique for dimensionality reduction in supervised learning for classification. Okay, so once again, it's a technique for dimensionality reduction, but it works for supervised learning for classification. Remember, PCA worked for unsupervised learning scenarios. LDA works for supervised learning for classification. Okay, so let us see how this works. Now we have said that in the PCA this is unsupervised learning, so data has no labels, and you find a direction Z, which maximizes the variance. Okay, so that was the objective in PCA. If you are doing supervised learning, you have labels. If you are doing supervised learning, you have labels, right? So your training data is already classified as blue and yellow. So the objective in supervised learning for classification, when you want to find a better direction, is a little bit different from what it was in the PCA. Here what you would like to do is you would like to find a direction Z. Along which the separation of the blues and the yellows is as clear and as wide as possible, and within each group the points are as closely clustered together as possible, right? So this would be great if you wanted to run a classification model. This kind of data would be terrific to run your classification model on, as opposed to this. So when it comes to dimensionality reduction in supervised learning for classification, you have two objectives. You would like the direction to be such that the two clusters are as far as apart as possible, and within each cluster the points are as closely huddled together as possible, right? Makes sense? Okay. So what is our goal? To recap, what is our goal when you want to do dimensionality reduction in supervised learning for classification? What is our goal? Our goal is to extract features in which the distance among classes is maximized and variation within a class is minimized. This is exactly what I said, right? So we want to identify features, we want to extract features, not identify, we want to construct. That's a better word. We want to construct features such that distance among classes is maximized and variation within a class is minimized. So this sort of an objective makes sense. The objective of LDA, which is also called NDA, Normal Discriminant Analysis, or Fisher Discriminant Analysis, these abbreviations refer to the same algorithm. Extracting such features or directions is the objective of these techniques. Okay, so that is what we want to do. We understand exactly what needs to be accomplished, and how to go about doing it is what we need to see. Okay, so now this diagram again summarizes what we saw in the previous slide. We have to find a Z so as to minimize in-class distances and maximize inter-class distances, right? How to capture this mathematically, into an optimization problem is what we are going to look at now. Can you create a suitable mathematical objective function that captures our intention and optimize with respect to Z? That's the question, right? And you can pause this video here and think about how you would go about doing this. But this is going to be our goal. Simultaneously maximize the separation of means and minimize in-class variance. That is how we are going to define the problem in mathematical terms. Okay, you want to minimize the in-class distances. That means you are going to minimize the in-class variance. Within each class, you are going to minimize the variance. Okay, and simultaneously you are going to maximize the separation of means. So this class has a particular mean, this class has another mean, and what you want to do is maximize the separation between these two means of these two classes. Okay, so you're going to do this simultaneously maximize the separation of means and minimize the in-class variance for each class. Okay, so let us put this in the next few slides. We are going to put this into equations and see how to go about that optimization. Okay, so the next 3-4 slides are going to be dedicated to the math. Okay, the objective of the math is pretty clear. Maximize separation of means and minimize in-class variance. And let us go through the math to see how it can be accomplished. Now I have simply picked it up from the internet, and I will go over the steps. There is not much for me to add to it. I will explain the steps to you. What I will do though is I will point out the key steps in the derivation, okay, where there is some amount of innovation or some amount of thought that has been put into how to go about it. Okay, so suppose you have two classes. I'm going to do this for binary classification. Suppose you have two classes C1 and C2. You find their means mu1 and mu2, right? These are labeled classes. So within each class you can find the mean mu1 and mu2. And let us say you have the sample counts for the two classes as n1 and n2 respectively. Now our initial space is d-dimensional. So basically every vector x has d components to it, right? So the components or the coordinates along d axis, that is what the vector x is. What LDA is going to do is seek a direction z, like we have done earlier. We are going to seek a direction z which basically tries to achieve the mathematical objective that we are going to set for it. Projection onto the direction z, as we discussed earlier, is simply the dot product, okay, of z transpose x. Last time we were doing x transpose z. It is the same thing as z transpose x. I am using z and z interchangeably, right? So this is the projection. This is the projection of each point on this direction z. Now, if you project the means in this direction, you have m1 and m2, which are of course z transpose mu1 and z transpose mu2, whatever, z transpose mu1 and z transpose mu2, because mu1 and mu2 are the means of the two classes, right? Okay. Now we are going to capture our objective in a mathematical equation, okay? We want large distance between the projected means. So the distance between projected means is m1 minus m2 square. Okay. That is what we want to be large. We want this to be large, and we want small within class spread, right? So the variance within each class, the variance within class 1 is over all points x that belong to class C1. What you are going to do is compute the variance. This is the projection of a given point x. This is the projection of the mean. So when you subtract the projection of the mean from the projection of that particular point x and square it, you get the variance along this direction for all points within class C1, right? Similarly for class C2. The total within class variance, therefore, I am going to simply add this and this. This is the in-class variance for class 1. This is the in-class variance for class 2. And the total within class variance is simply S1 square plus S2 square. Right? Okay. The Fisher criterion defines the objective function as a ratio. Remember, we want to maximize this, we want to minimize this, and therefore if I took the ratio of these two, I could say that we want to maximize this ratio, right? So maximizing this ratio would involve maximizing the numerator, minimizing the denominator, right? That is exactly what we want to do. And therefore we define the Fisher criteria. We define the Fisher criterion simply as seeking to maximize this thing, j of z, and you want to maximize j of z being defined in this particular manner as a ratio, right? So you can look at it for a moment, trying to maximize the distance between the means, trying to minimize the total sum of within class variance, and therefore in a way trying to maximize this ratio, This is known as the Fisher criterion. Look, it is true that you could have defined other criteria as well to achieve these particular objectives, right? So you could have said, I want to maximize this, and I put a negative sign, and I want to minimize this, and together you add them up and try to do it. But you know, the way you define the criteria should be such that it allows you to come up with a mathematically tractable solution. And that is where the importance of the Fisher criteria lies. Okay, so I have put a red star over here to tell you that this required some amount of thought, and by defining it in this way, it's going to make our solution mathematically tractable. It is going to allow us to solve the problem, okay, as opposed to coming up with some another criteria that may broadly meet the same goals of maximizing one thing and minimizing another. This makes sense, and this is mathematically tractable as well. Moving on. So how do we optimize that? Okay, so let's look at the numerator. The numerator was m1 minus m2 the whole square. That's equal to this, right? And by factoring out z transpose and expanding, we come up with this quantity, right? So z transpose got taken out, and because you are taking a square, effectively you are essentially taking z transpose this times this transpose z. This is exactly the same as this, right? These are derivation steps. It's just math, so I'm not dwelling too much on it, not doing it myself. Now I'm going to define the between class scatter matrix, which I denote by SB. I denote by SB as this matrix. Okay, this is a matrix. This is a row. This is a row vector. This is a column vector. This is a row vector, and this thing I am going to define as the scatter matrix, right? The scatter matrix SB. And therefore, m1 minus m2 square simply becomes z transpose SBZ, where SB is the between class scatter matrix. Defining this scatter matrix is a key step, and therefore I have put a star over here. Okay, this is again a derivation. You can look at it at leisure. You can look at it from any source. I am going to walk through it just to point out the key steps and to see and to show you the innovation, or to show you how things are cleverly chosen to meet your objective. That is the purpose of me running through this derivation. Okay, now you look at the denominator terms. S1 square is nothing but summation over x belonging to the class C1 of z transpose x minus mu1 square, right? And again, I'm going to simplify it in this manner, right? And I'm going to define the matrix x1 as x minus mu1 times x minus mu1 transpose for all points that belong to class C1. Okay, so now I'm this calculation pertain to the distance between the two classes, the distance between the two means. That was this calculation. Here I have moved on to within class. Okay, within class, and I'm looking at class 1 first, and S1 square I have simplified by defining a matrix S1 like this. So therefore S1 square becomes Z transpose S1Z, right? Similarly, S2 square becomes Z transpose a similar matrix S2Z, and I define SW as S1 plus S2, and therefore S1 square plus small s1 square plus small s2 square simply becomes this quantity right here. Okay. This again is a key step. Remember, SW within class scatter matrix is S1 plus S2, which allows the simplification of the sum of the in-class variances to be simply defined as Z transpose SWZ. Now substituting the numerator and denominator in J of Z in the Fisher quotient, you get this ratio Z transpose SBZ divided by Z transpose SWZ, where SB is the between class scatter matrix and SW is called the within class scatter matrix. Okay, so you're left with this ratio. This is known as the Rayleigh quotient. Okay, so therefore what is our optimization problem? We want to maximize this ratio. Subject to Z transpose SWZ being equal to 1. Okay, now again, this is a key step and I'm going to put a star over here. But this is a key step. In PCA we said we put a constraint Z transpose Z equal to 1. We said that we would deal with unit vectors. Here we are saying that Z transpose SWZ equal to 1 without any loss of generality, because it would still optimize over all possible directions. But what it does, it makes the optimization simple. So this is a key step as well. The Lagrangian therefore becomes, this is what you want to maximize with given this constraint. So you define the Lagrangian. We take the partial derivative with respect to Z as we always do with the Lagrangian. We set it equal to 0 and dividing by 2, we get the equation that the best direction has to satisfy this matrix equation. SB times Z is equal to lambda SWZ. Now the next step is, of course, you are going to pre-multiply both sides by the inverse of SW, and therefore you get that SW inverse SBZ is equal to lambda Z, right? And in other words, the optimal discriminant directions are the eigenvectors of this matrix now, SW inverse SB. Notice SW inverse SBZ equal to lambda Z, and therefore the optimum discriminant directions are the eigenvectors of the matrix SW inverse SB. So you take the inverse of the within class scatter matrix, pre-multiply it with SB, that is the between class scatter matrix. Once you have this matrix, you find its eigenvectors, and the top eigenvectors are the top optimal discriminant directions. Okay. Once you substitute the eigenvalue equation, this gives the closed form solution Z equal to SW minus 1 mu 1 minus mu 2, right? This is the optimum Fisher discriminant direction. This is the optimum Fisher discriminant direction, which is going to yield maximum separation between classes and minimal in-class variance. So I know I have breezed through this derivation. The derivation is available at a million places on the internet. You can look at it at leisure. My purpose in showing this derivation was to tell you about the key steps. Okay, and my purpose in showing you this derivation, rather than just letting you look at it later, was to show you how the correct choices of constraints, how the correct choices of the objective function can make the problem tractable while capturing the essence of what you wanted to optimize. That is exactly what has been done in the LDA in this Fisher discriminant in the Fisher method to find the optimal Fisher discriminant direction. Once again, they emerged as the eigenvectors of a particular matrix. Terrific. Okay, I put a star over here. Should have put it earlier. Well, I think defining the constraint is a key step over here. Defining the constraint is a key step here. Rather than saying Z transpose Z equal to 1, rather than going with unit vectors, you are going to define the constraint in this manner, which is what leads to this elegant solution right here. Okay. So what have we done? What we have done is we have found the optimal direction Z, which gives maximum between class separation, and minimum in class variance. That is what we have done. Given the data, this direction Z can be found. Okay. This works for the problem of supervised learning for solving classification problems. Okay. So you basically find the eigenvectors corresponding to the top eigenvalues. You limit the number of features and therefore use simple models. You can, if you had your initial dimension was 500 features, you could restrict your problem to maybe top 100, 150, whatever it is, whatever makes sense to you. Limit the number of features by finding the top 100 eigenvectors corresponding to the top eigenvalues. And again, because these are symmetric matrices, if I go back a step, I can show you, or you can do it yourself. You can see that the matrix whose eigenvectors you are trying to find is a symmetric matrix, because the scatter matrices themselves are symmetric, and therefore the eigenvectors are going to be orthogonal and give you good results. Okay, so all the objectives are met just as they were met in the PCA. With clever definition of the objective function, with a clever definition of the constraint, you could actually come up with this solution for the supervised classification learning case as well. Okay, so that is the LDA. I want to spend just a couple of minutes talking about kernels, because they also have to do with selection of features. Kernels are basically mathematical functions that transform data into higher dimensions to make your analysis or your problem solving easier. So if you are dealing with classification, it will make your classification easier. So here the guiding principle is not trying to minimize the number of variables. Here you are trying to add more features so as to actually make your data separable in the case of classification. This is exactly what I said. Projecting data into higher dimensions can make it separable. It can also make your analysis easier. And the type of kernel used, the type of mathematical function used to transform data into higher dimension depends upon the model that you are working with. So the kernel would be different for SVM, support vector machines, which we are going to see. It could be different for PCA, Gaussian, and so on and so forth. In particular, we are going to extensively look at kernels when we talk about SVMs in the next lecture. But here I want to just tell you what kernels are. Okay. Kernels that you use, the mathematical functions that you use, could be any of these. It could be linear, polynomial, radial basis functions, and so on and so forth. And the ones that you choose depend upon what model that you are working with. So for SVM, they would be a particular type of a kernel, and so on and so forth. Right? I have just given an overview. I have introduced you to the terminology without getting into too many details. The details of kernel are model specific, so we cannot make too many generalized statements. We will have to look at kernels in the context of a specific model, and the model that I am going to talk about later, where we will talk about kernels, is the SVM, a very important classification method that has to be taught as a part of any machine learning course. Terrific. That brings me to the end of this lecture. It has been a long one. So let us see what we learned in this lecture. We said that feature engineering pertains to manipulation of data or features to get better results. Number one. We said that there are various pre-processing techniques to fix issues in data, right? So issues in data, we saw how we could fix issues in data. And then we looked at the PCA and LDA mechanisms for feature extraction. Remember, there was a logical thought process to how we went about this. We said we wanted to do feature extraction. That means we wanted to do dimensionality reduction. Okay. So we wanted to minimize the number of features. We said that rather than just plucking some features, we would do feature extraction, meaning create a smaller number of features that would give us the best results for our models. We defined what we wanted to do, what we meant by the best features. We said these would be features where the variance or the separation between data points was maximum in the case of PCA. And then we formulated that in mathematical terms to show that these features or these directions were actually the eigenvectors of the covariance matrix in the case of PCA. In the case of LDA, the objective function that we wanted to optimize and the constraint was a little bit more complicated, but we were clever enough to define that. And we also showed that the LDA directions were also eigenvectors of a different matrix. So this is what we have studied. The optimization in both cases used the Lagrangian multiplier approach. What changed in the two cases, PCA versus LDA, was the choice of the objective function and the constraint. Great. I have some questions for you, as I always have. So try to think about them rather than putting them in ChatGPT or some such tool to get the answer. These are thought exercises. So you would benefit if you applied your own thought rather than asking some AI engine online to apply its thought. If your original data is not linearly separable, can it be linearly separable in lesser dimensions? And how about vice versa, right? So you had, let us say, 500 dimensions in which your data was not linearly separable. If you took only 100 out of those 500 dimensions, would your data be linearly separable in only 100 dimensions? Your choice of which 100 to choose. Is that possible? And how about vice versa? If your original data is not linearly separable, can it be linearly separable along its PCA? Okay, so now I know that PCA does not deal with supervised learning. I am asking you a generic question. If your data was, let us say, it had labels and it was not linearly separable in the original dimension, can you come up with a PCA direction along which it is linearly separable? Is that possible? My third question is, does PCA increase or decrease the bias and variance errors of the model? So for example, if you did a PCA, you came up with a few features, you came up with a few directions. Will that increase the bias and the variance errors of your model as opposed to using your original data? That's question number 3. Question number 4. If you gather data on the age and 100-meter sprint speed of males between ages 25 and 60, what would the principal component of that data look like? I want you to guess the vector without doing any calculation. Okay. So this is the data, age and 100-meter sprint speed of males between ages 25 and 60. What would the principal component of that data look like? Your choice on what units to choose to measure these, but go ahead and come up with a guess on what the PCA, the primary principal component would look like. Don't do a calculation. That's question 4. Okay, that's all I have for today. Thank you, good luck, and I'll see you next time.